Hello! Hi everyone. For those of you that are still talking, need to stop. Okay, if you're still getting beer, you should have got here sooner. If you're not in a seat, also should have got here sooner. Those of you that are in seats have probably been here before, so that's good. Good for you, good for me, good for Astronomy on Tap. How many people have been here before? Oh, that number just keeps growing. Must mean something's going right, despite my best efforts. Okay, so those of you that haven't been here before, you get a little quick rundown, and quick is sort of based on how talkative I'm feeling, so we'll see. But those of you that have been here before, just drink your beer. Okay, so what can you expect in Astronomy on Tap tonight? Well, first off, welcome. The introduction is happening right now, so if you're not following along at this point, here's your opportunity to catch up. All right? So the way that it works, I'm going to walk you through the sort of schedule for the evening, and then we'll talk about some of the details afterwards. All right? So the first talk, so we'll start out, we'll have a talk by Dr. Benoit Côté. Okay? He's a postdoctoral research associate at Michigan State in the Department of Physics and Astronomy, and he's going to tell you all about the cosmic origins of the atoms that are in your body. Okay? So we didn't just get here magically, all right? Turns out that there's a lot of science that explains how we got from a universe that had nothing in it to the universe we have today. Okay, so he'll be walking you through that process. After that, we'll take a break. Pro tip, you haven't been here before, this is your opportunity to work on the trivia-based raffle game, okay, which I'll explain here in a moment, so keep that in mind. After that break, we'll have a second talk for the evening. Dr. Arash Bahramian, I apologize, Arash, I'm a jerk. You're up here, the lights are bright. He's also a postdoctoral research associate at Michigan State in the Physics Astronomy Department. He's going to talk to you about telescopes, how they work, and then also how they work at wavelengths that aren't just visible light. Okay, so the light you're used to seeing every day, that's one type of telescope, but there's a whole bunch of different kinds, a bunch of different ways we can observe the universe around us. Okay, so you hopefully by the end of the night you'll walk out understanding some stuff about that. Then we take another break. Again, you have the opportunity to work on the raffle. Okay, I'll talk about that in a moment. Then we'll wrap up the evening with a Q&A session with all the local astronomers or physicists who are in the room. Okay, they'll come up to the front. The way that works is there's some blank pieces of paper over here and some pens. If you have any questions, either about the talks, extension questions, or questions about astronomy in general, write them down on one of those pieces of paper and put it in the box that says "Got a question." Okay. Put it in there, and then at the end of the night, we'll go through and answer as many as we can, okay? We'll pick out the good ones, throw out the bad ones, okay? If your question doesn't come up, it's just because we didn't have time, okay? And then after that, we'll do the raffle drawing, which is what most people, I think, stick around for. And so we'll talk about the raffle now. So how does the raffle work, okay? During the breaks, we're going to put up a set of slides. Those slides have questions on them. You're doing your best effort to answer those questions correctly. The topic tonight is going to be topics related to the talks, okay? So there'll be questions related to telescopes, questions related to chemical evolution, the chemicals that are in your body, so on and so forth, okay? You do your best work, try to answer those questions. Make sure you get your name on it, first and last. The raffle entry cards are over there, okay? So you'll see something that says name with a blank, and then 10 numbers with answer options next to them, okay? So that's the answer sheet, all right? I want to make sure everyone follows that. If you don't put your name on it, or you don't put your last name on it, I will crumple it up and throw it away. Okay? So it turns out that there's occasionally someone with the same name as you in this room. I think if you have one of those names that's common, you're experienced in this area. Okay? If you can be absolutely certain you're the only one in the room with that first name, go for it. Okay? But we'll see. And then. Last step, hope you win. If you want to know what the prizes are tonight, we have a few things. Okay, so we have a coffee mug. So it's a sort of a beverage theme set of prizes tonight. A coffee mug that when you put coffee in it, the constellations appear. It's pretty sweet, right? It's magical, doesn't take much. This is actually a loose leaf tea infuser. That's a space capsule with an astronaut attached to it. So the astronaut hangs over the side. It's adorable. It's fantastic. Okay. And then, if you're not into caffeinated beverages, this is a set of shot glasses with all of the animals that we launched into space. If you win this, you can look up whether or not they made it back. Spoiler alert, not all of them did. So, I don't know if PETA was around at that point, but it's a different issue entirely. Okay, and then in addition to that, we also have two $25 gift cards, one to the Loft and one to Taps 25. Okay, so if you just want cash money, that's about as close as you can get to cash money. All right. I all know you drink, so that is probably the most useful prize. All right. So, any questions about that? Doesn't matter. Moving on. Okay. The donation box is the other element that will happen during the break. So, Astronomy on Tap is completely donation supported. The way that we do the donations every month is we have a head-to-head battle. Okay, so you vote with your money. Right? Any donation works. No donation is too small. The battle this evening is going to be Nikola Tesla versus Thomas Edison. Okay, if you know anything about electricity, you might have an opinion on this matter. So there's this handsome fellow, Nikola Tesla, and then this guy. So, do what you will with that. So that's your option. Last time we did Wonder Woman versus Guardians of the Galaxy, and Wonder Woman pretty much won in a landslide, which is pretty awesome. Go Wonder Woman. Bringing in 2.4 times as much as Guardians of the Galaxy. Okay? And again, those donations keep us, this is always a free event as long as we keep bringing in some of that donation money to help support the costs of this event. Okay? So that's that. Probably one of the grad students will be bringing that around during the breaks. Okay? So, the next Astronomy on Tap event, if you're already enjoying yourself and want to mark your calendar, August 9th, 2017, again, it's going to be here at the Loft. And one of the talks will be about the Great American Eclipse that's happening on August 21st, 2017. Okay? And then the other talk will be about something else. All right. If you're confused why we'll be having a talk about the eclipse in August, pay attention. Okay? There is a solar eclipse happening in August 21st. If you've lived under a rock up to this point, stop drinking your beer and listen. All right? August 21st. I also realized I've been talking about the eclipse for the last few months. How many people know what an eclipse is? Total solar eclipse. Okay, I appreciate the people that did not just go, oh, yeah. Okay, the way that this works is the moon gets in front of the sun and casts a shadow on the earth. That shadow is only in certain spots, which is why you can only see the total eclipse on this bright orange path. Okay, the rest of the path will see a partial eclipse. Here in Lansing, it'll be about 84% coverage, which is still pretty impressive and better than anything Michigan has had in quite some time. Okay, so it's cool if you can get to the path, do that. Probably every hotel you could ever want to book is already hooked up. So find a friend, sleep outside, get to know nature, whatever you gotta do. Correct? So that's happening. If you want to watch it safely, we have these. They're Astronomy on Tap solar eclipse glasses. If you want a pair of these, throw an extra $1 donation in the box, okay? I'm going to be going around during the breaks and giving these out. You don't have to give me cash directly, but I will take it take it on your honor that you'll donate in the donation box, okay? So $1 for those if you're interested. All right, if you need more science in your life, next week check out Biology on Tap. It's happening on Tuesday, July 25th here at the Loft. I read their description, and they're doing something related to hyena penises. So that's different than what we do here. And maybe you're into that. No judgment. So consider checking that out. Follow them on Twitter, like them on Facebook. How many of you are Googling that right now? I don't need to know. All right? So, with all of me yapping for all of that amount of time, it's probably best that we move on to the science for this evening. So I'm going to get Dr. Benoit Côté to come up and get ready. So give us just 1 minute to switch over the slideshow. And then once we're ready to go, I'm going to ask you to get a big round of applause. So hold tight for just 1 minute. All right, please welcome to the stage Dr. Benoit Côté. Big round of applause. Good, thank you very much. Is everybody hearing me well? Okay, very well. Perfect. All right, so I'm pretty happy to be here, and especially because I can present and drink a beer at the same time. I think this is quite amazing. You don't get that often. So here I go. So we'll talk about the about the evolution of chemical elements in the universe. So all the atoms that we see in the universe, on Earth, on us, has come from somewhere, and I want to show you and explain to you how we can create these things with some echo from a robot. All right, so let's start with a classical image of the evolution of the universe. So it all started with the Big Bang right here, where all the matter of the universe was very hot and very dense. Then following this Big Bang, the universe started to expand, and as the expansion is going on, the gas started to cool and collapse to form the galaxy that we see today. Now here is a simulation of how that evolution actually happened. You start with pretty much nothing, and then as you move forward in time, if I start the video, oh, it used to work. Oh, it's happening. Was that happening? Yeah. So we start with basically nothing, and then as you move forward in time, gravity starts to push the gas together, and they clump and they form this nice structure that we call cosmic web or cosmic filament. And this is simulating a very large area, a very large volume of the universe. So each of the bright dots that you see, and the big ones are actually a galaxy or a group of galaxies. So this is a very big volume of the universe. And if we were to just take a section of this simulation and look at one of the bright regions, we will see that it is actually consisting of many, many galaxies. So that is a real image from the Hubble telescope. Each of the bright things is a galaxy, and you see in this large context how these large systems are actually forming. So galaxies tend to form together in what we call cluster because of gravity. Now, it's already beautiful to look at, but if we were to look inside each of the galaxies, we can see nice things like stars, nice nebula, and planets. So, as crazy as it sounds, all the nice universe that we see today, like here, started from nothing. And just gravity made all this work somehow. But the evolution of the universe is not only about the formation and evolution of galaxies, stars, and planets. It's also about its chemical composition. So what is the matter made of? And that is a good question, especially if you start to look at the chemical composition of the universe just after the Big Bang. It was only composed of hydrogen and helium. These are the two lightest atoms in the periodic table. But today we know there's many elements. There's carbon, nitrogen, oxygen, silicon, iron, there's gold, there's silver, there's many, many elements. So how did we came from that universe, from this universe, while we are creating all these new elements? And that's what I want to explain to you today, tell you how we can create these elements from scratch and come up with this universe. Briefly. So during this presentation, I will say atom and elements many times, but they basically mean the same for me and for the purpose of this talk. So don't be too confused. I mean the same thing. So if we are to speak about the elements, we need to go back to the basics. Here is the periodic table of the elements that you have probably seen in the chemistry class. And for those of you who have a very bad memory of this, I'm sorry. But we need to go back to this to understand how it works. And I promise I will keep that very simple. So if you were to look at each of the atoms and look deep inside at their core, what we call the nucleus, you will realize that it is actually composed of little particles called protons and neutrons. So they compose all the elements. And the trick, so the periodic table can be very complex, but one of the very basic rules is the following. The number of protons determines what is the atom. That's the only thing you need to remember from this to understand the evolution of the elements in the universe. It is very simple. So if you were to take the first element, hydrogen, it's one proton.
Then you look at the second element of the periodic table, you have helium. So you have 2 protons. You, of course, as you increase the number of protons, you bring more neutron, but let's not focus about the neutron right now. Let's look at the proton. So this is very basic. If you look at carbon, that's the element number 6. It has 6 protons. Oxygen, it's the element number 8, 8 protons. I think you start to get it. And now we start to understand how it is possible to create a universe from just hydrogen and helium to a universe with full of elements. The only thing you have to do, you take these 2 elements, and then you just keep adding protons on them, and then you're going to create all these elements. Now this looks easy, that's the theoretical thought, but it is actually quite hard to do this. And the reason for that is there is a force called the electric force that prevents protons to get close to each other. It's pretty much once you try to bring 2 protons together, it's like if you were bringing 2 magnets with the same pole. There's a kind of repulsive force. But this can happen anyway because we do see all these elements. So now I'm going to explain to you what is nuclear fusion, which is a process of creating new elements by merging protons together. Keeping it simple, these are 2 protons that want to create nuclear fusion, and the electric force, which is a repulsive force, will be played by this spring. Now the hands will play the role of the nuclear force, which is an attractive force which will be able to keep the protons together. Now the nuclear force is stronger than the electric force. But in order for that force to be activated, you need to bring the protons very close together. So if our 2 protons are getting close together with a speed that is not great enough, what's going to happen is they're going to get close, but the electric force is going to push them apart. Thank you. I'm so glad I spent too much time on this part. Okay. But if the protons are actually getting together in front of one another with a very high velocity or speed, they will get close to each other to a point where the nuclear force will be activated, and then they hug each other, and the protons stay together. And that's it. I hope. Right. So yeah, and once this is happening. The electric force still tries to push the proton apart, but the nuclear force is always stronger than the electric force, and therefore this will stay together and you will have created nuclear fusion. Nuclear force is stronger than the electric force. I need to practice my timing. So how did I do it earlier? Oh, it was working, so I just need to be patient. And you need to be patient as well. Nice. All right. So here are 2 spiral galaxies, one here, and because of gravity, these galaxies are getting closer and closer together, and they're going to spiral one around another. I don't know if it's possible to say that. But at some point, they're going to merge their star, merge the gas, and become just one bigger galaxies. And that's how galaxies get bigger in time, by merging with each other. So that has absolutely nothing to do with what I was saying. I just thought that when I was creating this slide about nuclear fusion, I didn't know if it was going to be boring or not. So I thought it was going to be boring, so I just said I'm going to put a nice video to create some sort of balance. So let's go back to nuclear fusion. So the only place in the universe where that can happen, because remember there's the electric force that prevents protons from getting to each other, but if you can do this, you get nuclear fusion. But it's pretty hard, and the only place in the universe where that is happening is in the center of stars. That's the only place where that can happen. And a key aspect of nuclear fusion is when you merge atoms together, you do create energy and special effect. Nice. And this energy is actually why you see light in stars. So when you look at stars, the light that is emitting is the result of the nuclear fusion. Because when you combine atoms together, you create new elements, you create carbon, you create oxygen, you create iron. It does produce a lot of energy, and that's what you see. Now I would like to open a parenthesis to let you know that the famous equation by Einstein, E = mc squared, can be applied in that situation. So when you do nuclear fusion, for example, if you combine 2 helium atoms to form a barium atoms, well, if you do that, you will realize that the product of the nuclear reaction is lighter than the two individual projects taken together. So you lose mass somehow. But this mass is not lost, it is just converted into energy. And that equation tells you how much energy is generated by the nuclear fusion. M is the mass that has been lost during this process. You multiply that by c squared, where c is the speed of light, and then you get your energy generated by nuclear fusion, which explains the light coming out of stars. Now, once you created all these elements, carbon, iron, all that in the stars, they do not stay inside the stars forever. They actually come up by going back into space. Because stars eventually dies, and they're going to eject these elements by either stellar wind, so you just have a star and the outer air are just getting ejected, or in a more spectacular way, they sometimes explode as a supernova. And when that happens, most of the element that has been created by nuclear fusion is going to be expelled in the surrounding medium in outer space, inside the galaxy. Which brings me to the life cycle of stars, which is a very important aspect when it comes to understanding why we have so many elements on Earth today. So you start with gas here inside a galaxy, and because of gravity, this gas is going to collapse to form many stars. Now these stars are going to live, they're going to create new elements by nuclear fusion, and then they will explode at the end and release these elements back where they formed. So now this gas is now enriched in new elements like nitrogen, like silicon, and now this gas that is now enriched with new elements is going to form again a new generation of stars to start the cycle all over again. So that's how it's working. And as you move forward in time, the gas is always getting more oxygen, it's always getting more nitrogen, because you always have more stars that are putting more of these elements. Now going back to this plot that we showed, me showed at the beginning of the presentation, the important thing to realize is the life cycle of stars and the process of creating new elements is happening in this galaxy, it's basically happening in all galaxies. So everywhere in space, when you see galaxy, you know that elements are being created. And I just realized I can use this to change the slide. Better now than never. Okay, so now if we were to look at just one galaxy, yes, it works. So let's just take, for example, this galaxy, just because I have this nice video on my computer, and if we were to look at this galaxy, just make a zoom on this region, you will see, a lot of gas, but if you zoom even more, you will start to see region that form stars. So this is gas collapsing to form stars, and all the little white dots are stars that have been formed. It is, of course, all simulations, but this captures pretty well this process of the life cycle. What you see here is the gas being transformed into stars. And the important thing to remember from this slide, beside that is nice because it moves, is that the life cycle of stars is actually happening while the galaxy is evolving. So the bottom line is the chemical evolution of the elements, the process of creating new elements, the life cycle of star, all that is happening everywhere at all time, in all galaxies. And if you were to take this galaxy, look here instead, or here, you will see the same thing. And also it's happened at all time. It happened in the past, it's happening right now, it will happen in the future. That's a very universal process. So now that we have picked this galaxy and this star-forming region, let's look more in detail into one of the stars. If we just take this star here, we know that stars are forming out of gas that has been enriched by previous generations of stars. And once the stars has formed and start to shine because of nuclear fusion, you still have some gas that is surrounding the star. And this gas is going to rotate, form what we call an accretion disk. And eventually this disk is going to be unstable and create these little clumps that you see here, that will orbit around the star. And once everything is cleaned up, it will form a nice planetary system. And let's say it is our own solar system, it creates planets such as the Earth. Now in this grand scheme, it's very nice because we know that by looking at this, we know that these stars have been created by from gas that has been enriched by stars. But because planets also form out of gas that has been enriched by stars, we can say that the Earth and everything that is on the Earth, including us, all the atoms in our body, have been cooked inside the stars one is their life. So if I have to take an atom inside me, I know that at some point in time, it has been at the center of a star doing nuclear fusion. So I think this is very, very fascinating. Maybe it's biased because that's what I do for a living, but I think it's nice. So to finish, I would like to tell you where we actually come from, what is our cosmic origin. So this is the human body, and of course we're full of molecules and all that, but if we break that down into individual atoms, well, we see that we have a lot of hydrogen, not too exciting, but we have a lot of carbon and a lot of oxygen. And now with recent simulation and the theoretical advance in stellar evolution, we know that carbon basically comes from stars that are similar to our sun, or a little bit more massive, but that's where you produce most of the carbon. The interesting part is not all the stars produce the same element. If you have different stars, you will produce something else. For example, oxygen, we know that it is mainly produced by stars that are about 10 to 30 times more massive than our sun. So it does come from somewhere else. And if you think about iron, which is in our blood, this comes from a special type of supernova explosion, which is shown right here, which is not this explosion made or just something like this in the distant past. And because of the life cycle of stars and the fact that stars all mix their matter that has been ejected, all these stars have died and have mixed their elements with the surrounding gas, and this has collapsed to form stars and eventually us. So I hope I've convinced you that the ultimate origin of the atom in our body is stars. We are actually stardust, but what I find even more fascinating is that because of this, we know that we come not only from one star, but we come from many generations of stars. And that's my end punchline, so I hope you enjoy. And I'll be right back.
Awesome. Thank you so much, Benoit. All right. So, all right. What we're going to do now is try to take questions from the audience. I have some indeterminate amount of cord up here. So if you're far in the back and you want to ask a question, why don't we try to meet somewhere in the middle? Okay. If you're up front, you can just be lazy and sit in the middle. All right. So questions. All right. So this one here first, and you're close.
How many stars had the God create Earth?
Oh, that is a very good question. I actually do not know the answer for that. But that's something I'm currently working on. It's kind of difficult to tell because to answer this question, we need to know once the element has been ejected in the galactic gas, in the gas inside the galaxy, before it forms stars, you need to understand what this gas is going to do. Is it going to stay there and then recollapse, or is that going to be mixed with something greater that is surrounding? It's quite a difficult question to answer, but that's a very, very good question. Clearly, more than one. Actually, more than three.
Other questions? All right, there is one in the back. I'm going to try to make my way in that general vicinity. Sorry, people. If the cable gets stuck, help me out. Okay. Nice.
Is there a difference in the expediency rate between the stars in the northern hemisphere and the southern hemisphere?
Sorry, can you repeat this?
So is there a difference in the expediency of the rate in the northern hemisphere stars?
In terms of element production?
Yes.
No, it's actually the universe is kind of uniform that way. So as soon as you look at the stars, you know it's going to create some basic elements. So it's anywhere you look, south or north is going to be the same.
Awesome. Thank you.
Yeah.
Any other questions? Yeah. Okay, there's one over here.
Thank you. What is the cosmic background radiation?
So this is when the well, let me. I have a slide for this. Well, not really, but okay. The background microwave radiation. So initially here, when you go very far in the past, at the beginning of time in space, you have the Big Bang, and what you're asking is, what is this? That is the cosmic microwave background. And what's happening is at the beginning of the universe, well, first of all, I have to say that when you look far in space, you look back in time. Because the speed of light is a constant, and it's very fast. Like it's a 300 million meters kilometers. 300 million meters per second, right? I hope so. So it's crazy fast. So even if it's fast, the universe is so big that if you look at something that is very far away, it still takes time for the light to come to you. For example, if you look at something that is 1 billion light years away, that means it takes 1 billion years for the light to reach you. So as you look far deeper into space, you're actually looking more into the past. And at some point, you're going in that direction by looking even further into the space. And at this point, you're going to hit this, which is the cosmic microwave background. And this is the moment in the universe where the light started to freely travel. Because before that, the universe was so dense, right after the Big Bang, then light was sort of trapped into the matter, and the light was not able to travel anywhere. So if we were not able to see anything after that, before that point, because the light could not reach us. But at some point, the universe became less dense, which is here, and then all the light that has been trapped started to travel, and now there is some sort of light that we can detect today. Maybe it was a too long answer, but the short story is this is the most distant light we can observe, which is a fossil of the early time of the universe.
Okay. What about over here? Was there any questions over in this general vicinity? Oh, do we have questions from the live stream? All right, I'll come back that way. It's complicated, but I'll do it. We're going to go to the live stream because we've never done that before.
Okay, this is a question from Jack Blitzen. Do we have any estimation for how much material or mass is fused in the center of our sun per second or per minute or per some unit of time, basically?
Oh, I should know this. I do not. But I'm just going to take advantage of this to throw an impressive fact. I don't know how much mass it is, but I guess we can convert that using the Einstein equation. But if I remember correctly, in just 1 hour, the sun, the light, the energy that reached the Earth by the sun is enough to power an entire year for human consumptions. So I guess you can take that number and use Einstein to figure out the math. That's a good question. It's a really technical question. I do not know this answer.
That's tricky math off the top of your head. I can't get it.
Pretty hard question.
All right, there was another question back here somewhere. All right, we'll go to the far corner.
So, if you go to your last slide,
With the human body?
yes. Let's talk about the iron. Yeah, so you were saying that you're only able to create iron from supernova. I was under the impression when you get to the more massive stars that iron is kind of hard to limit and you can fuse together.
So yes, iron is the limit that you can fuse together, but you do reach the point of creating iron.
Okay, yeah, so my question is about what's after that. Right?
Oh.
So,
Right. So you mean how you create heavier elements?
yeah, especially because like here you're saying that it takes supernova to create iron, which is not even halfway in terms of how massive the atoms get, right?
Right.
So,
okay. For the other, I don't have time to go into this, but for the heavier element, for example, gold and silver and all these precious material, these are created not by nuclear fusion but by neutron capture processes. Because once you reach iron, if you start to create nuclear fusion with irons or heavier elements, you're not going to generate energy as you do with nuclear fusion with lighter elements. You're actually going to consume energy from your environment. So that's why stars, when they reach an iron core, they collapse because they use their source of energy to balance the gravity. So how you create this heavier element is by shooting. You take a seed, for example, an iron, and you just throw a bunch of neutrons, and then you throw the size of the atom like that, and the neutrons are eventually going to decay into protons. So while you do this, actually you kind of being able to create these heavier elements with more protons. And this happens either in a coconut supernova for massive stars, or when two neutron stars, which are the remnants of massive stars, merge together. So you have two neutron stars that merge together. You have a lot of neutrons who bombard your seed, and they decay and produce heavy elements.
Okay, I know there are more questions, but for the sake of time, we're actually going to move on. So let's thank Benoit one more time. Okay, Benoit will be here the rest of the evening, probably drinking more beer. So if you do have more questions for him, please feel free to corner him and ask questions until he runs out of the energy to answer you. Okay? So what we're going to do now is... hello? That was confusing. We're going to take a break. And during the break, I'm going to put up the trivia raffle slides. Okay? Those will go up. Okay. Okay, that's probably my fault. I probably did something bad. So the raffle cards are over here. Okay, so pick one up. There's some pens. Share pens. Pass them around. Feel free to work on it with your friends, so on and so forth. The other thing that's going to go around is the donation box. So if you want to donate and help support the event, please consider throwing some money in there. I'll also be going around with solar eclipse classes if you want to make sure you're prepared for the eclipse. So otherwise, get some beer, and we'll be back in about 15, 20 minutes. Hello! It's probably louder out there than it is up here. It's good for me. All right, shh. Hello? Yes, wonderful friends of mine who are still talking. They're on the side. Okay. So what we're going to do now, thank you so much for donating. Hopefully you got some eclipse glasses if you wanted them. If not, come find me at the next break. Hopefully you filled out the raffle entry, or you're waiting to get more information during the next break. All right. So please make sure you do that if you want a chance to win. And please, at this point, please give a big warm welcome to Arash.
Thank you very much. So my name is Arash Bahramian. Thanks, Devin. And so I'm going to talk about telescopes and how they work, but not a deep dive, basically a bunch of shallow dives, because every day we hear about a new telescope and new observatory around the world. Why are there so many, and what is different about them? And so you've seen things like this, which is a normal telescope that we can buy. And then this, which is basically a gigantic version of the same thing. It's the same concept. It has a mirror, and it has an eyepiece here. But instead of a human looking through, there's a CCD that takes the image. And then we have this one, which is the same concept, but in the space. And all of these three follow the similar concept. But then we get to the weirder ones, these ones. These are the radio telescopes. Where is the eyepiece? Where is the mirror? How do we observe space with these things? And then we get to weirder ones like this one. How can this be a telescope? This looks like an alien artifact. And so these are the type of telescopes that I'm going to talk about and see, and just go overview in what each of them do and what we learn from them. So the core principle that since humans have looked up to the sky has been that we have a source in the sky, phenomena in the sky, or a star, galaxies, planets, and these are emitting different messengers. Now, I call this messenger because light is one of them, and light is the oldest form that we have been observing. But it's not the only one anymore. We have theorized for almost a century existence of other messengers, and just recently, in the last few decades, we have started observing them, and just the last 2 years, a new one, we started observing a new one. So what I'm talking about is, besides light, we also get energetic particles. In these particles can be protons that, for example, very energetic events in the space kick out protons, neutrons, other weird particles, and some of them reach our atmosphere, and we can observe them. Then besides that, we have gravitational waves, which we have just started observing. So all of these are messengers from the cosmos, and we are trying to observe these with different observatories across the planet, sometimes outside in space. So I'm going to talk about light and electromagnetic emission, but maybe I talk a bit about something else as well at the end. So electromagnetic emission is considered that to have a dual nature. So what it means that it shows both particle-like behavior. So, for example, it bounces off other particles, so it has momentum and it behaves like a particle bouncing off. But at the same time, it also shows wave-like behavior. So, for example, if you create two sources of wave for example, on a lake, on a puddle, you will see this interference pattern. And light shows the same interference pattern as well. So it shows wave-like behavior, but the momentum, the bouncing off, also shows particle-like behavior. And so this will affect how we can observe them, and we will exploit both of these natures to actually understand what the cosmos sent towards us. Another thing is that we have different types of light all across the electromagnetic spectrum. We have radio waves, infrared, visible, ultraviolet, X-ray, and gamma rays. They all have the same speed. What is different for them is frequency and wavelength. And their energy. So the radio waves have very low energy, visible light has higher energy, X-ray and gamma rays have extremely high energies. So that's the basic principle why we need different detectors for each of these different technologies to catch different types of light. Now, let's start with the most familiar one, the optical light that we can see, and we have been studying the cosmos through optical light for hundreds of years since Lippershey and Galileo made telescopes and looked up. So the principle is simple. What we use is mirrors and lenses to focus the light. Focusing optical light, infrared, and ultraviolet is relatively easy. We can do it with lenses and mirrors. And so we bend it, and we can gather a lot of light from the space, and we can look by eye or use other things like photographic plates or CCDs to actually capture this and try to study it. So the detectors that we are using currently are called CCDs. And previously, we used photographic plates, which were just a surface of chemicals that was surfaced with a lot of chemicals that react differently to different wavelengths of light. So if the green photon hits that surface, it makes a different reaction, and so that was how we could see with photographic plates. Now, with the CCDs, the system, the way it works, there is the surface of the sensor that photon hits. So this is the particle nature of light that we are using. So photon hits the surface of the sensor and reacts, and the sensor reacts and releases an electron. And we basically detect that electron, and based on that, we can take pictures of the sky. And this is the same principle that we use in our phone cameras or laptop cameras. So this is the basic principle for infrared, optical, and ultraviolet. Now, one problem with ultraviolet is that our atmosphere blocks a lot of ultraviolet. So most of the ultraviolet, almost all of the ultraviolet observatories are in the space because they cannot be on the ground. While optical and infrared observatories, some can be on the ground, some should be in the space as well. So this is the most familiar one. So this is the first three images that I showed you. This is a very basic telescope, same principle, a very massive mirror with no cylinder around it, and the detector at the bottom, and that's a human for scale. And this is the Hubble telescope, which is the same thing in space. And for scale, Hubble telescope is almost the size of a school bus. So why do we need Hubble telescope in space? The reason being that the atmosphere perturbs the light. So if we put these telescopes in space, we will remove that filter. And sources of optical light, infrared and ultraviolet is pretty much most of the things we see in the universe: planets, stars, dust, hot gas in the galaxies, and so on. Now, radio waves. So radio waves, we can bend them easily, we can focus them, but not with mirrors and lenses, but instead with other material, but the same geometric concept. So that's why the radio dishes that you see, they are all concave and look similar to a mirror in a telescope. But the problem is that radio waves are very weak, so we cannot use CCDs to detect them. Because if a radio wave hit the surface of the CCD, it was not going to react. There's no reaction happening. So we need to use something else. And that was why when people started exploiting the wave nature of light. So the way it works, the converging works the same. The optics are the same, that the light hits a concave surface that can reflect that type of light, and you collect that. But at the end, what you have is a receiver which gets the electromagnetic wave and converts it into voltage. And so based on that voltage, they get the signal. So this is why radio telescopes do not have mirror, and we use, or CCDs, they use a different interpretation for detecting the radio waves. And there are different types of radio telescopes around the world. We have ALMA, which is a collection of multiple dishes, which they all work linked together, and they give us great signal and great resolution. And we have Green Bank Telescope, which is the largest steerable construction around the world. And to give you a scale, this is bigger than the Statue of Liberty. And it moves, it rotates, it moves up and down, and that is another radio telescope that we use. Source of radio waves can be pulsars. Pulsars are a dead remnant of stars, massive stars, that rotate really fast around themselves, and they have strong magnetic fields. So pulsars can have strong radio emission. Also, black holes in the core of galaxies can have a lot of radio emission. And at the same time, cold gas in the galaxies, they also can have radio emission. So this is the type of things we learn through radio waves. Okay, so radio, infrared, optical, ultraviolet. Then we get to X-rays, which are the high energy ones, and they are very hard to focus. So CCDs work, not the same CCDs as optical. We have a different combination of material, but the same concept works. So the photon hits the surface and it releases electron, and we can detect it. But they are very hard to focus, so we cannot use a mirror because mostly the X-rays will go through. So we need to use another technology. Also, they are blocked by the atmosphere. So that is the other problem, that the atmosphere blocks them, and so we need to put these observatories in space. First of all, the optic problem, we fix it, we address it by using cylinders. So these are magnetic cylinders that what they do, they force the X-ray photons to be focused towards the detector. So it is the same principle. We are trying to focus them, but it is very hard, and we need to use a very odd combination of cylinders, concentric cylinders, to actually make them focus towards the detector. So this is the technology that is used, and we need to put it in space. And so these are the X-ray telescopes in space. This is Chandler X-ray Observatory, which is, it has the highest X-ray resolution among all the available X-ray telescopes in the sky. However, this is NuSTAR Observatory. It works in harder X-rays. So Chandra works around here in this spectrum. Chandra works around here, NuSTAR works around here. So NuSTAR sees things that Chandra doesn't. Now, the thing about this long arm is that focusing hard X-rays is harder than soft X-rays. So soft X-rays being lower energetic and hard X-ray being more energetic. So focusing those is harder, and you need a longer focal length to focus them. But the problem is that as we need to put these in space, we cannot make this massive few tens of meters telescope and launch it into space all by itself, as it is. So the way they overcame that problem was that they made this arm retractable. So they launched it compact, it went up, and it opened up. And it got to the focal length that it needed. And that's why it looks like this. So the cylinders that focus the light are around here, and the detectors, the CCDs, are here. And that's how NuSTAR works. Sources of X-rays are among the most fascinating things in the universe. That's what I say because I study them. But the reason for them to be fascinating is that because they are on the edge of our understanding. So we have neutron stars, which are the densest form of matter in the universe. So we cannot replicate them on Earth. We cannot get anywhere close to the density of matter in neutron stars. And we can study them in X-rays more effectively than any other wavelength. So that's amazing. Black holes, especially when they're interacting with other stars. So this is a black hole pulling matter from another star that came close to it, and we can study these again with X-rays only, effectively. And finally, massive black holes in the center of galaxies, we can study those again with X-rays. So this is an optical image, this is an X-ray image of that black hole in the core. So this is what we can learn with X-rays. And finally, there we go. Gamma rays. So gamma rays have been the toughest challenge so far in the electromagnetic spectrum. We cannot bend them, and they are blocked by the atmosphere, and detecting them is really hard because the CCDs don't work as effectively. So it's really, really hard to study them. So what have they done? They have tried to develop a new technology for detecting gamma rays. And the way it works is the concept is kind of similar to CCDs, that you have a surface that gamma ray hits and interacts, and you can detect the results. But because gamma rays generally go through these without interacting, you need to change and do more surfaces. So what they do, they make a big box with multiple layers of the sensor. And so this sensor, if it is made of a specific material, that if the gamma ray hits, it will release an electron and a positron. A positron is basically an electron with a positive charge. So if a gamma ray hits one of these surfaces and it releases electron and positron, they will go through the rest of those layers, but they cannot go through the bottom well, which actually catches them and makes sure and knows where they hit on the well. So what we have, we know which layer was hit, and we know where electron and positron fell on the bottom well. So based on those, we can actually trace where the gamma ray is coming from. So we trace it. Instead of focusing, instead of getting a CCD image, we trace where the gamma ray is coming from. And that's how we make these images for gamma rays. This is the direct way to detect gamma rays. There are indirect ways that I'll show in a minute, but this is the direct way. And this is, at the moment, one of the most successful gamma ray telescopes that works with this principle is Fermi telescope. And this white box over here is exactly that detector. So it has layers and layers of this material that is supposed to get the gamma rays, and at the bottom it has a well that actually catches all the positrons and they can detect them. So this is a space-based detection and the direct detection of gamma rays. I say direct because we are actually seeing gamma rays themselves. But gamma rays are very energetic. and we can actually detect them indirectly. The principle is Cherenkov radiation. So when something moves in an environment faster than the speed of light in that environment, it creates a radiation known as Cherenkov radiation. This is an example of it. So what you're seeing, this is not astronomical, but so what you're seeing is a nuclear reactor. And at this moment, there is nothing happening. The moment the reactor starts, you see this blue radiation. The reason being, neutrons are leaving the reactor and hitting the water. But the neutrons are moving faster than the speed of light in that water. And because of that, they create Cherenkov radiation. Same happens in our atmosphere. So what happens is that gamma ray hits the particles at the top part of our atmosphere. And because of that, it will create, those particles start moving faster than the speed of light in our atmosphere. Here's a demonstration of that. So what you're seeing is that the gamma ray hits here, and all the red points you see are actually particles that start moving faster than speed of light in that environment. All the blue things that you see are the Cherenkov radiations because of that. And so more particles, it's like a chain reaction. So more particles start moving, and finally you have a substantial amount of Cherenkov radiation that we can actually detect on Earth. So this is how we can go after Cherenkov radiation. So Cherenkov radiation is actually an optical emission, but it has a very specific signal. And detecting it is difficult. It's very faint because it's a higher part of the atmosphere and it's faint. And it needs to actually pinpoint where it's coming from, we need multiple telescopes. So the way they do it is with telescopes like Veritas, this is one of them. So it works in optical, but the principle of the observation is different. It just looks for a specific type of light. So it just looks up, and the moment it sees that blue light, that's it, it found it. And Veritas and telescopes like these need to be multiple dishes. So they have multiple dishes with mirror, and based on that, they find where it is in the atmosphere. So they triangulate it, basically. Now, why do we need to see gamma rays? Gamma rays are among the most energetic things in the universe, and things that send these and that produce gamma rays are really exotic, and we don't fully understand them. One of them being Crab Nebula. So Crab Nebula, one of the wonders of the night sky, has a neutron star in the core of it. And that neutron star rotates rapidly around itself. And it emits gamma rays that we can detect. The reason, and it's relatively close by, so we can detect them easily. Other things that create gamma rays are supernovas and black holes, very massive black holes that are pulling matter from around them. So that's why gamma rays are important for us to understand what is happening around us. So that was, and this is the sky in gamma rays. So the Fermi telescope that is outside our atmosphere, this is how it sees the universe and tells us. So what you see, this is the galactic disk. This is our galactic center. And you can see there are a lot of sources of gamma rays in the sky. And if I recall correctly, I think that is the Crab Nebula, or that. So that is why it's important to study gamma rays. So this was just a tour to show why we have all these different telescopes and what they can show, how they work briefly, and what they can show us. And that was pretty much it. If you have any questions, I'll be happy to answer. Thank you.
Awesome. Thank you, Arash. Do we have questions for Arash? Saw a hand go up and then right back in. We're going to go again.
Can you explain what kind of neutrinos we're getting when there's a coronal mass ejection? Because it seems to come in phases, like there's a pulse and then the electrons and so on.
So coronal mass ejection from the sun is a massive event that it is complicated and it has multiple signatures. So there is the optical signature, which we can see some of the observations for the sun that NASA has done. You can see the mass leaving the sun, so you can see the rapid ejection from the sun. But, so what it has, so first of all, it has the light because there are hot particles that emit optical light. Besides that, there are energetic particles like protons, charged particles, that actually, they also have their own signature. So they hit our atmosphere and they have their own signature as well. So we see them in optical, and sometimes if they are hot and they are created under specific conditions, they can actually produce X-ray emission as well. So we can sometimes see X-ray emission from them.
Other questions? There's one over here.
On the right-hand side there, what kind of telescope is that?
This one?
Yeah.
Okay, so this is, thank you very much. So this is a telescope that I did not discuss, but I have actually backup slides for it. So all of these telescopes you see are the ones I talked about. That's a radio telescope, that's optical and infrared, X-rays, gamma rays on the ground, gamma rays in the sky. This is a gravitational wave observatory. So it's a different type of messenger. We are not talking about electromagnetic light, we are talking about gravitational waves. So what are gravitational waves? Simply put, what happens is that, here we go. So what we have is that we have two massive objects merging, so two massive black holes merging and creating a ripple in the space. So to play it again, so you have two very massive black holes rotating around each other, and when they merge, they create in this ripple throughout the space-time. And this is through the space-time, so it changes, it basically shrinks and stretches our distances in time. And so what happens is that the signal after that merging, it starts to go all around the universe. And so what happens is that we, at that location, we are going through these ripples. So Earth actually experiences these ripples. And so that observatory's job is to actually detect that signal. So the way it works, they have two beams of light that have the same frequency, the same phase. So imagine two ropes that they are moving with the same frequency, and they are up at the same time and down at the same time. And so all you need is a tiny bit of change in the distance, so in the length of one of these arms, to actually detect the gravitational wave. And that's what they do. So the gravitational wave just slightly shrinks one of these arms, and then what you see is that the signal that they receive from these two waves changes, and that changes gravitational waves. That was a too long answer, but I enjoyed it. Thank you.
For the record, I told Arash he didn't get to talk about those tonight. So I'm pretty sure he paid someone in the audience. All right, any questions? Oh, Danny.
This is only like.
Danny, is this a real question?
Just a really quick answer.
Yeah. Okay.
I don't actually want to hear about it, but I just want. Do you have backup slides for neutrinos too?
Neutrinos, I have, but I know because I know I never get to them.
All right. Man comes prepared. All right. Oh, right there.
Nope, never mind. He said it was good though.
Okay, so I'm not an astronomer. I don't understand why X-rays can pass through mirrors but can't pass through the atmosphere.
So there are two things that happens with X-rays. So X-rays are very energetic, and they pass through most matter unless they are really thick that they can absorb So we cannot, so any material that we put in front of them, so if we want them to bounce off, they won't bounce off, they will just either go through it or they will get absorbed while they're going through. So what the cylinders do, they basically direct them. So they are magnetic cylinders. So as the X-rays go, because of the shape of the cylinders and because of the magnetic field, they basically force the photon, the X-ray photon, to slightly move down. So they don't bounce or go through them. Sometimes they do. They actually, some of the X-rays go through these cylinders. But what the cylinders do, they just basically, if the photon is going this way, they slightly just nudge them down. They're like, go this way. So that's all they do. And so this pushing down is what the cylinders do.
There's a follow-up to that, though. How does the atmosphere stop the X-rays?
So our atmosphere has at different levels can absorb the very energetic photons like gamma rays, X-rays, and ultraviolet. And part of it is because of the density, and part of it is because of the nature of the elements in that part of the nature of the material in that part of the atmosphere.
The atmosphere is also a lot thicker than most of this. You really have a question in the back? Is this just a joke? No. I'm just kidding. I'm coming. Sorry. This is going to be the last one, by the way, so good. No pressure. Where did you go? No.
During your presentation, you mentioned the Chernobyl radiation moving faster than the speed of light. Could you provide more depth to that explanation how it's traveling faster than the speed of light?
Sorry, can you speak louder?
Could you provide more depth into how the radiation is traveling faster than the speed of light?
Oh, yes.
It's shrink up radiation.
Yeah. So this is the speed of light in the environment, not the speed of light in vacuum. So speed of light in vacuum is the speed limit of I don't know, tell the photons, not me.
Okay, we're going to pause there and get more questions for Arash. Give him a big round of applause right now. Arash will be around during the break, so just like you cornered Benoit, you can corner Arash. Okay? Sorry, this board is so long. So what we're going to do now is we're going to take one more short break before we do the Q&A. So you have a chance, if you haven't filled out the raffle already, you will have a chance to do that. I'll put the raffle questions back up on the slideshow. So we'll do that. If for some reason you didn't get Eclipse classes and you want some, come see me. I'll get some for you. The other thing I want to point out, we have a couple of questions so far for the question box. So in order for us to do a Q&A session, we actually have to have Q's for our A's. Okay? So if you have any questions related to astronomy, that gentleman over there is writing one down right now, hopefully. Probably not appropriate. But please write a question down, put it in the box. If you do anything astronomy, physics related, we'll do our best to answer them. Okay? So please give another beer if you need it, and we'll be back in about, we'll say about 10 to 15 minutes or so, okay? And then we'll do the Q&A, and then we'll do the raffle. Remember, you have to be present to win the raffle, because I don't have any way of contacting you. That's why there's no spot for email or phone number. You have to be around to win. All right, we'll be back in just a few minutes. Hello. Howdy. Those of you that are still here, thank you, but also shut up. I mean that in the kindest possible way. It's like a, when I say shut up, it's like I'm saying I love you to each and every one of you. If that makes you feel better. All right. Okay. So what we're going to do now is the Q&A, which you have to suffer through until you get to win these classes. So put up with it. If you don't want to wait, leave. Okay. Can I get all of the astronomer, physicists, astrophysicists, if you identify yourself as such, please come to the front of the room and fill up this space up here. You tend to like to pile next to that pillar really awkwardly, but like, There's all
We're
of
just
this
awkward
space.
people,
Should we
Devin.
go up here so the camera can
No! No!
Okay. So one of you has to grab that microphone and sort of be in charge of passing it around. Sorry for coughing into the microphone. Okay. Is this all of you? Did Mark leave? Oh, there's Mark right there. We have a Dr. Mark Côté. Okay. All right. If we could just bring the chatter, just that's better. Thank you. Okay. All right. I'm going to read this one because somebody took the time to write it. That's rude. I apologize. If this is your question. If we are all made of stars, does this include Donald Trump? No. I don't know what he's made of. It's not star stuff. Okay. Anywho, let's not get too. All right. Here we go. How do gas clouds emit radio waves? Arash? No.
So one of the things that allows gas clouds, very cold gas clouds, to emit light is rotational and translational mode. So what it means, you have molecules. They're really cold. So you have molecules of, for example, ammonium. And so what happens is that some of these atoms in these molecules start rotating, oscillating, or they rotate around the molecule axes. And these rotations and vibrations emit emissions that are really, really faint, and they are in radio frequencies, and we can observe those. And these are signatures of those elements. That's how we observe them. So, for example, we observe carbon monoxide, and we observe ammonium and chlorine, these things, actually.
Cool. Thank you.
I have a question for Arash. Why didn't you just raise your hand right away?
Just hiding in the dark. Okay. Here's one. Have you thought about changing the name of this event to Astronomy and Hill? No. Thank you. Okay, here we go. If I remember correctly, at the last AOT, there was mention of 2 new orbital telescopes coming online soon, and we should be super excited about them. What are they? Somebody want to chime in? I know of at least one.
Yeah, I know one of them that actually about a year ago I gave a little talk about this, JWST. It's a James Webb Space Telescope, and it will actually be launched in October of 2018, so mark your calendars. It's going to allow us to see in the infrared. It's actually one of the largest telescopes, I think it is the largest telescope that we'll ever be putting into space, and it's got a bunch of, it's probably 21 meters, I think, in diameter. And each of it's made up of a bunch of these honeycomb-like structures that make up the mirror, and they're all covered in about a golf ball size amount of gold, and that gold is really good at reflecting infrared light. And so the infrared light from whatever we're looking at, that's the farthest we'll be able to see in infrared, those light waves will actually come to the mirror and they will bounce off the gold detector part, and then it'll go into the actual detector of the telescope. And once it goes up into space, it actually has to unfold because it has to have these giant solar blocking shields. And so that whole thing is going to unfold. It's going to be like 4 stories high. It's probably the size of it. And yeah, it's going to be really cool. So we're going to see some really amazing stuff with it. And I'm really excited for it, for one. But yeah, JWST, if you just Google it, you'll learn a lot about it. And I don't actually know what the other one is.
Telescope guy knows.
I think the other one is NICER, so NICER. which was launched around a month ago, and now is actually operational. And actually, yesterday they announced that it passed all its tests and it's completely functional. So NICER is a small cube that is a telescope that is attached to the International Space Station, and its job is to study neutron stars. So it works in X-rays, and it studies neutron stars, and its main job is to do timing. So it gets pulsations of neutron stars really accurately. Pulsations of neutron stars tells us about the rotation of neutron stars, which tells us about radius of neutron stars. And based on that, we can learn what is inside of neutron stars. We don't know yet what is inside of neutron stars, and we cannot replicate them on Earth. So the best way is to make better telescopes to study them.
Cool. All right. This one says, thank you for the explanation of CCDs, but what does CCD stand for? Students want to answer that question?
Charge coupled device.
All right. That's a lesson about when you use acronyms. Yeah, right.
There's also a or like an observatory called the VLA, and it stands for Very Large Array.
Some classic astronomer brilliance. Okay, we're not just going to name acronyms now. It's not the game. Okay, here's one. I like this one. I feel bad that I've never noticed this before. Is it just me, or does the expanding universe diagram look a lot like a pint glass? Yeah, it does. A pint glass. Now I have to make a talk at some point where I turn it and fill it with it.
Welcome. Now someone needs to actually make a glass that looks like
Thanks, Jamie.
someone go to
Okay.
and make some money.
Okay, yeah, something about getting to the bottom of that pint glass. It's meaningful. All right. Nope. Oh, who is this Chandra person that has a telescope named after them? Let's spread the wealth a little bit.
So the complete name is Chandrasekhar. He was an astrophysicist, and what he did was he actually expanded our knowledge into what we know about remnants of stars. So when stars die, when they run out of hydrogen to burn, and not just hydrogen, other materials to burn in their core and in their shells in the core, what happens is they either abruptly or calmly, they disperse most of their crust and outer shells into the space, and what you're left is a remnant, is a tiny remnant, which could be a white dwarf or a neutron star or a black hole. And Chandrasekhar was one of the people that actually made most of the predictions of what we expect in these stars, how it happens, and what we can learn about them. So that's why this telescope was named after them, because this telescope, one of its main goals was to study these remnants, and so it was named that way.
Okay, we're going to do, I think, maybe just one more, which means I have to decide. Sorry, we don't have time to do all of them tonight. There's a ton of good questions, which is awesome. We're going to do... Okay, we'll do this one because it sort of sticks to the theme. Is there an advantage to having telescopes further from the Earth, say near the moon? Question. And Arash does not get to answer this question. Oh.
I'll answer it. The answer is yes for some telescopes. JWST, which was mentioned earlier, which is the James Webb Space Telescope, that is really the successor to the Hubble Space Telescope, is not going to be in orbit around Earth. Yeah, get away from the speakers. It's actually going to be in orbit around the Sun. And the idea is, since it's an infrared telescope, you want to keep it cool. Because if it gets too warm, it makes its own infrared light, and that weakens what the telescope can do. So you want to get it far enough from Earth so that Earth's radiation isn't heating it up. And that's one example of a telescope that you don't want too close to the Earth. And so it'll be gradually, it'll be out, past the Earth, farther from the sun than Earth is, and orbiting at the same rate as Earth orbits. So that's one example of, yes, sometimes you do want it as far from Earth as possible.
Okay, cool. Well, thank you so much, everyone. Please give a big round of applause for You should make a point to remember these faces. They're here a lot. They come out to support Astronomy on Tap. They know a bunch of information, so if you ever want to have a one-on-one conversation with a local scientist, please talk to them. Learn more about them, learn more about what they do. Okay. Sorry if I did not get to your question. There were so many tonight, which is awesome. We will have to revisit them in the future. Okay. So, I guess that's it. Just have a good rest of your evening. So, all right, I've done the joke before, it's not funny. Yeah. Okay, so, where's the box? All right, so what we're going to do, I'm going to shake this box up. So we're going to do the raffle now. What I need to kick it off, and what we normally do for the raffle is, unless we have something super duper special, we let you choose. So the first person gets the pick of everything, the last person, you get whatever the leftovers are. Just remember that every prize is awesome, and if you win, you're still doing better than most everyone else in. Okay, can I get someone in the front here to come up and grab the first one? Lewis! All right, dig around in there. Does it feel like yours? He's like, I crumpled mine into a ball. All right, the first prize goes to Reed K. Is Reed K still on the room? All right, Reed. Your options are shot glasses of animal shot into space, Constellation coffee mug, or the tea infuser space capsule. He's taking the shot glasses. We know what Reed does in his free time. We dig in there, mix it around. If you pull out a friend's one, and you know it's cheating. All right, next prize. Thank you, Reed. You can sit down. Next prize goes to David Miller. Is David Miller still in the room? All right, David. Oh, Reed, just so you know, Reed, pay attention for a second. I know it's exciting. You also could have gotten $25 gift cards. You're good? Okay. You're taking the coffee mug. All right, get out of here, David. Wait, you got to draw one. David took the coffee mug. Didn't even let me show them to him. All right. Next prize goes to Peter William Jennings. It's Peter William Jennings. It's still in the room. All right, Peter. You can either have the Space Capsule Tea Infuser or $25 to either the Loft or Task 25. Task 25 is now off the table. Can you reach in there and grab out one more? Don't cheat and look. Thank you, Peter. All right, Josh Franklin. Is Josh Franklin still in the room? Come on down, Josh. All right, Josh, you either get $25 to the Loft or the Astronaut Tea Infuser. Taking the Tea Infuser, all right. Well, hang on. I'm going to mix this a little bit. All right. Marcus Pruitt. Is Marcus Pruitt still in the room? Hey, right there, Marcus. All right. Well, that gift card, $25 gift, not the donation box. All right. Enjoy the $25. Come do an Astronomy on Tap. Buy yourself $25 worth of beer. All right. So that's all the prizes we have this evening. Thank you so much for coming out. I enjoyed this. This has been 2 years that we've been doing Astronomy on Tap, which is pretty awesome. Okay. I started this 2 years ago. I figured I'd get 50 people on average. And you guys have blown me away. It's been a lot of fun. I enjoyed doing it. Hopefully, I'm still up here in who knows how many years. And hopefully, I still get to drink for free. Cheers.